Achieving consistent human comfort requires engineers to account for far more than the simple volume of cold air moving through a room. True climate control is a product of high-precision thermal balancing. The consequences of poor design are significant. An oversized air conditioning system will cycle on and off too frequently, wasting energy and failing to dehumidify the air. Conversely, an undersized system will become overwhelmed the moment outdoor temperatures reach their peak. To find the correct equipment capacity, engineers develop a load estimate. This document serves as the mathematical foundation for the entire project, determining exactly how much thermal energy the system must remove to maintain stability. The primary challenge lies in translating unpredictable variables, like shifting solar angles and human activity, into a reliable numerical heat budget. Every source of energy entering or generated within the space must be quantified. Comfort is the result of a deliberate process. It involves mapping the invisible thermal physics of a space long before the building is even constructed. The process begins with a building survey to document physical realities. Engineers record the building's orientation toward the sun, the total area of exterior glass, and the density of the construction materials used in the walls and floors. These factors determine how the environment impacts the interior. Solar heat gain is often the largest external factor, as radiant energy from the sun pierces the glass and heats the internal surfaces of the room. We also have to account for the occupants. The human body generates heat through oxidation, a biological process measured as the metabolic rate. As people work and move, they contribute a continuous, measurable amount of thermal energy to the space. Secondary internal loads add another layer to the budget. Fluorescent lights, computers, and mechanical equipment all release heat, acting as persistent thermal sources that the cooling system must neutralize. The sum of these external and internal factors is known as the instantaneous heat gain. This represents the total amount of energy entering the space at any given moment. However, sizing a system to match this absolute peak gain would result in a massive, inefficient installation. Because of how buildings actually behave, the peak cooling required is often much lower than the peak heat gain. This discrepancy exists because the building's structure acts as a thermal sponge. Concrete, steel, and stone absorb and hold a large portion of the instantaneous heat before it ever affects the air temperature. This creates a time delay known as the storage effect. There is a measurable gap between the moment heat hits the building and the moment the air conditioning system actually needs to remove that energy from the room. This chart maps that divergence. Notice the sharp peak of the instantaneous heat gain curve on the left and the much flatter, delayed curve of the actual cooling load. The area labeled heat stored shows the energy being captured by the building's mass. By utilizing this storage effect, engineers can specify smaller, more efficient equipment that handles a smoothed out load rather than an extreme peak. Eventually, that stored energy must be removed. The pull-down load section indicates the period where the system works to extract the residual heat that has saturated the building's construction during the day. Accounting for this temporal delay allows engineers to design systems that are precisely calibrated to the building's unique thermal rhythm. Once the load is calculated, the engineer must determine the exact physical properties of the air needed to neutralize that heat. This is handled through psychrometrics, the science of the thermodynamic properties of moist air. It provides the technical framework for selecting equipment that can meet the specific needs of the space. This psychrometric chart visualizes the path to comfort. The RSHF line, or Room Sensible Heat Factor, connects the target room design point to the required supply air condition. It shows the exact state the air must reach to balance the room's heat gain. The process at the cooling coil must address two types of energy. It removes sensible heat to lower the dry bulb temperature, and latent heat to remove moisture. Latent heat is the energy involved in phase changes, like water vapor condensing into liquid on the coil. These psychrometric charts act as the operational map for the building, translating static calculations into a physical cooling strategy. When the load estimate is accurate, every variable, from the thermal mass of the walls to the metabolic rate of the people inside, works in concert with the mechanical system. In a well-engineered space, the massive effort required to maintain this balance remains unnoticed. The technology works silently to keep the environment stable regardless of the conditions outside. This same mathematical rigor is applied across entire urban centers. It is the unseen framework that allows thousands of separate environments to function simultaneously within a single city. This mathematical approach to heat management is a core requirement for making modern, high-density buildings both habitable and energy efficient.